The James Webb Telescope has discovered new clues about what happened before the Big Bang, challenging some current scientific theories. The Big Bang is a theory that the universe began as a very hot, dense point, and that it expanded and cooled, allowing stars, galaxies, and other structures to form. The theory is based on evidence such as Hubble's law, which shows that distant galaxies are moving away from us, implying that the universe is expanding. The age of the universe is estimated to be about 13.8 billion years old, but the James Webb Telescope has made an exciting discovery about what happened before the Big Bang. What really happened before the Big Bang? We invite you to join us to explore this exciting discovery by the James Webb. If you're interested in keeping up to date with news from the universe and its surroundings, subscribe to the channel, be sure to like this video, and turn on the notification bell. The cosmic microwave background radiation, CMB, is a faint radiation that fills the entire sky and is a remnant of the intense heat and light of the early universe. The uniform temperature of the CMB is about 2.7 Kelvin, with small fluctuations indicating density variations in the plasma. The CMB also shows that the universe was opaque to light until about 380,000 years after the Big Bang, when atoms formed and light could travel freely. The abundance of primordial elements such as hydrogen, lithium, beryllium, and boron matches predictions of the Big Bang nucleosynthesis. The galactic distribution reflects how matter has clustered under gravity over time, forming stars and galaxies from small fluctuations. The oldest galaxies are found near the edge of our observable universe, and galaxies have different shapes, sizes, ages, and composition depending on their location in history. The younger objects are closer to us, while the older ones are at the limits of the observable universe. The problem with what happened before the Big Bang is one of the biggest challenges in cosmology. The Big Bang theory describes how the universe originated in a hot, dense state, expanded and cooled over time, but does not explain what caused or preceded this initial state. Scientists have proposed several explanations, such as the Big Bounce, the periodic egg scenario, and the pre-Big Bang scenario. Each of these theories proposes different causes and events that led to re-origin of the universe. The pre-Big Bang scenario is based on the string theory, which is a framework that links all natural forces and particles. On the other hand, the boundaryless proposal suggests that our universe has no boundaries in space or time, and that the Big Bang is a soft zone when the size of the universe becomes very small. According to this theory, the beginning of the cosmos is described as a quantum fluctuation from nothing using quantum physics and a wave functions that encode all the potential histories that determine the structure and attributes of the universe. It is important to note that these possibilities are not mutually exclusive and may be compatible or complementary in some aspects. One of the major scientific goals is to find out how the universe formed, and the latest discovery of the JWST, the proto-galaxy cluster ever discovered, may help to achieve this goal. In theory, the universe has a hierarchy in how things unfold, and in the early phases of the hot Big Bang, all matter and energy were uniformly dispersed throughout space, with small perturbations superimposed on that uniform background. These oscillations are caused by the cosmic inflation that preceded and set up the Big Bang and exist on all cosmic scales, from the smallest to the largest. As matter and radiation interact and the universe expands, fluctuations on the smallest and intermediate scales have peaks and valleys in the density of time. Fluctuations in the universe can wax and wane, and the largest fluctuations on cosmic scales can be observed in the microwave background, which contains information about overdense regions that began to develop gravitationally. Gravity does not act uniformly throughout the universe, and its effect is restricted by the speed of light, which means that an overdense region in space will only attract nearby matter at a given time. The farther away matter is, the longer it will take to feel the gravitational pull. The size of the cosmic scales increases with gravitational attraction, from star clusters and galaxies to groups and clusters of galaxies. Once a large-scale region experiences gravitational attraction, gravitational collapse must occur for a bound structure to form, and at the center, receding matter must cause such collapse. The density of the overdense zone must increase approximately 68 times for the large-scale structure to stop decaying and begin to collapse. Eventually, a bound object composed of subcomponents that form a large-scale structure will form. The first formations to collapse are molecular clouds of gaseous dust atoms and dark matter, which give rise to the first stars and star clusters. The densest regions can take 200 to 250 million years to collapse, while regions with higher initial overdensity conditions can collapse in as little as 50 to 100 million years. Star formation emits radiation and winds that create complex environments and make it difficult to predict details about these early structures. The first massive galaxies in the universe form from this merger of these structures. Richly evolved galaxies have been detected 320 million years after the Big Bang, and the JWST is expected to reveal populations of immaculate stars and earlier galaxies on a broader cosmic scale. However, disordered physics plays little or no role in the size of individual galaxies. However, allowance must be made for continued stellar production, enormous stellar winds and radiation, stellar deaths and cataclysms, cooling and falling gas and other atoms, matter fusions and ionization, and the interaction of dark matter with normal matter. When it comes to the formation of galactic groups and clusters, these factors have very little impact, and the formation is largely determined by three well-known factors: the expansion of the universe, the magnitude of the initial overdensity on the relevant cosmic scale, and the interaction of multiple cosmic scales. Whatever happens inside a galaxy, sometimes derisively referred to as gastrophysics, has no effect on the creation and growth of galaxy clusters, only gravity matters. Before JWST, there were a variety of methods for discovering these galaxies. Throughout cosmic history, the simplest and most straightforward method was to identify a large number of galaxies that existed in the same field of view at identical redshift distances, but with significant velocity dispersion. The redshift method is used to discover and study distant galaxies in the universe. It is based on the principle that light emitted by moving objects is shifted towards longer wavelengths, for example, towards the red end of the electromagnetic spectrum. This phenomenon is known as redshift and is due to the Doppler effect. When a galaxy moves away from us, the light it emits is redshifted, which means that the characteristic spectral lines present in a spectrum are shifted towards longer wavelengths. This redshift can be measured by analyzing the spectrum of light arriving from the galaxy. Astronomers use spectrographs to scatter the light at different wavelengths and then examine these spectral lines. If they find a significant redshift in the spectral lines of a galaxy, they can determine that the galaxy is moving away from us and estimate the speed at which it is moving away from us. The redshift is expressed by the parameter z, which represents the ratio of the measured wavelength to the wavelength emitted by the galaxy. The higher the value of z, the greater the redshift and the greater the distance the galaxy is located. By measuring the redshift of many distant galaxies, astronomers can map the distribution of galaxies in the universe and study the expansion of the cosmos. They can also estimate how far galaxies are and obtain information about the evolution of the universe over time. The clustered galaxies were moving at velocities of several hundred or even a few thousand kilometers per second relative to each other. This method facilitated the discovery of nearby galaxy clusters, such as the Coma cluster of galaxies and the Virgo clusters of galaxies, which are heated, for example, by the collision of fast-moving gas clouds or by intense star formation processes that release X-rays. Thank you very much for watching the video. Remember to like and subscribe. This way you will be supporting the channel. And I'll see you in the next one.